Well, over the last many modules, we have discussed, not in a lot of detail, but we have discussed the working principles of the instruments used commonly in ultrafast dynamics, ultrafast spectroscopy. Now, we want to come back to the discussion that we originally started. We know a little bit about the instruments now, fine. What do you do with these instruments? What is it that you study? What kind of systems you study? So, once again the answer is that you can do a lot of things, and what we will do in the next few modules is that we are going to present a few selected problems that have captured the attention of a lot of researchers over the last few decades. To start with, we will talk about molecules, then we will present briefly about ultrafast processes that take place in semiconductor nanocrystals and metallic nanocrystals, and then we will go over and discuss, depending on how much time we have, some other techniques, because mainly now we are going to talk about results of your femtosecond optical gating and pump probe. So, next we are going to go on and talk about 2D IR spectroscopy, at least 2D IR and 2D electronic spectroscopy, and then let us see how it unfolds. So, what we do usually using these instruments and using these techniques is that we try to study chemistry beyond ground state chemistry. Now, most of the chemistry that goes on all around the world for a lot of time is that when you say chemistry, what you really think is that you mix something with something else and produce a new substance. So, in fact, if you read ancient textbooks like that by Ladli Mohan Mitra, you see that he has written that I like chemistry because chemistry is the only science in which you can create something new, and that has really been the focus of chemistry. But then there is a lot of chemistry that can take place not in the ground state, but in the excited state, and it is taking place all around us, as we have discussed earlier. So, what we try to do using these lasers and all is that we try to understand chemistry that takes place beyond ground state, and many times we use this chemistry beyond ground state to initiate reactions and see how they proceed. Okay. So, in this module, what we will do is we will remind you of what we had perhaps presented little sketchily in the first 4 or 5 modules. You might remember that we had said that excited state phenomena are reflected in certain properties, spectral properties of the molecules. To start with, if you are doing fluorescence spectroscopy, one thing that you learn first of all is Kasha's rule. Kasha's rule says that a fluorescence spectrum is a mirror image of, should be a mirror image of the absorption spectrum, and it holds very nicely for well behaved fluorophores like pyrene. Fortunately, it does not hold good for many molecules, because if it did, then we could not have made a living out of being fluorescence spectroscopist in 2019. If every spectrum would have been a mirror image of the absorption, then it would be very nicely organized and absolutely boring. Fortunately, Kasha's rule is a rule that is meant to be broken in many cases. So, most of our research goes into studying this rule breaking game. So, what happens when the rule is broken? What happens when a new state is produced post excitation? Then the certain signatures are obtained in the spectral and temporal features. And as we had discussed earlier, so we will not repeat now, the driving force of this excited state processes is change in electron configuration. As chemists, we know that it is electron configuration that decides reactivity. It is not very difficult to understand that when we perform an excitation, of course, electron configuration changes. That is why you go from an electronic state to another electronic state. And here, let me repeat, at the risk of saying it several times perhaps in this course, I do not know, I do not remember if I said it, but many times we ask people to draw Jablonski diagram, they draw it, and then we ask what is going from S0 to S1, and everybody says electron. That is wrong. So, please, we should be actually conscious about this. Electron goes from some molecular orbital to some other molecular orbital, not necessarily from HOMO to LUMO. HOMO to LUMO very often is not even allowed. Some occupied molecular orbital to some unoccupied molecular orbital, that is where the electron goes. Okay. The molecule goes from S0 to S1 or whatever it is. Please do not forget S0, S1, T1, Sn, Tn, all these are electronic states of the molecule determined by and large by the configuration. I say by and large by the configuration because even configurations talk to each other. You have what is called configuration interaction. For a brief introduction to this phenomenon, one may refer to our course which is now online. It is available freely in YouTube, the NPTEL course on symmetry in chemistry. So, there we have discussed in detail the case of naphthalene, and there we have talked about how configurations of same symmetry can interact. But roughly we can say that it is a configuration determines a state. So, it is not just one electron, all the electrons together, which orbitals they occupy. That is what determines the state of a molecule. Remember, electronic state is the state of a molecule and not of one particular electron, right. So, that I am sure I have repeated myself, but it is an important point, and I see that even people coming for faculty interviews have no idea about this. So, I think it is better that we say it, especially as it is hoped that this course will reach a wider audience, right. So, what are the signatures of excited state processes? First of all, if you look at fluorescence spectra, this let us say, if you can read the x axis, this is actual spectra recorded in our lab many years ago. X axis is in wavelength. So, if you go from left to right 325 nanometer to 575 nanometer, from left to right energy decreases in a reciprocal manner. So, this spectrum is the mirror image spectrum. So, that is the characteristic spectrum of the locally excited state, and the red shifted band that you get is a characteristic of the what I like to call nascent state, the state that is formed as a result of the excited state reaction or excited state process, whichever you want to call it. Okay. So, what happens is when you excite, this is the state that is populated initially. Over time, this state depletes not only to go back to the ground state, but also to populate the state responsible for this red shifted emission. So, now if you record fluorescence decays in the high energy side of the spectrum, or as we like to call the blue side of the spectrum, and the low energy side of the spectrum, as we like to call red side of the spectrum, then what do you expect to see? The species responsible for emission in the high energy side has an additional deactivation pathway, and that is the excited state process. So, you expect a fast decay of fluorescence in the blue end of the spectrum, like what is shown here, and the state responsible for this emission is not even there at the moment of excitation. It grows over time as a result of the excited state process that depletes the locally excited state. So, you see an initial rise followed by a decay, of course, an excited state has to decay eventually. Okay. So, if you go back to our chemical kinetics knowledge, this is sort of this red emissive state is sort of like the intermediate. Remember how the population of the intermediate evolves over time, it goes up and then goes down. Reactant goes down all the way and the product goes up all the way. Okay. So, this state is like an intermediate, that is why there is a rise followed by a decay. And then using these two, I think we have discussed this, one can construct the time resolved emission spectrum, whereby you can see that you can see how the emission spectrum itself evolves over time. And this is a very useful thing to know, as we are going to discuss, not in this module, but maybe a couple of modules later. And nowadays, in many instruments, you do not really need to record the steady state spectrum and the decays separately. If you use two-dimensional detectors, as we have discussed earlier in this course, you can actually get the time evolution of the emission spectrum. In the next module, we are going to show you an example of such a piece of data, where you record the spectra first, and then from there you obtain the decays. Okay. Now, fluorescence is not the only technique that we have studied. The commonly used technique which we have whose components we have studied in great detail is a pump probe or transient absorption. Here what you do is you excite your sample by a laser pulse, an intense laser pulse, which causes an excitation to some higher excited state, and then what you do is you look at the excited state population that is going to decay with time. How do you follow the time evolution here. If you remember very basics of spectroscopy, one can use your Lambert-Beer's law as we are going to see, but before that this is how you do the experiment. This is your sample, this is the pulsed pump light, the light that is responsible for populating the excited state, and along with that you put in a pulsed probe light. Probe light is usually of much less intensity compared to the pump light, because the job of it is just to probe, it should not disturb the excited state population too much. So, what you do is you monitor the absorbance of this probe light. Let us say, well, probe light can have any wavelength, but let us say we have a probe light which matches an absorption of the excited state. Now, as we know that absorbance is epsilon CL. So, if you can follow the time evolution of absorbance of this wavelength, then that will give you an idea of time evolution of the population or concentration of the excited state. And you might remember we talked about this in one of the earlier modules. So, just recapping, because it has been such a long time. What you do is that you look at this probe pulse, right, and you basically change the delay between the pump and probe pulses. So, if the probe pulse arrives before the pump has arrived, in this scenario what will happen? It will not be absorbed, because you have chosen a wavelength, let us say, that is absorbed by the excited state, but not by the ground state. I am not talking about multiplex detection here, I am talking about using a monochromator and a detector, and I am pretending as if I have only one wavelength of probe light, not a spectrum. So, the absorbance is there is going to be 0. Now, suppose you have decreased the time delay a little bit, it is still 0, absorbance is still 0. Now, you keep on changing the delay, there will be a time when you will achieve time 0. Time 0 means the delay of the pump and the probe are exactly matched, and that is when the probe light will encounter the maximum possible population of the excited state and absorbance will shoot up. Okay. So, in this cartoon, the circles denote the absorbances measured at specific delays, and this line shows you the time evolution of the excited state population. So, if the pump pulse is delayed further, it will come a little later. Now, what will happen? Population would have decreased, let us say, from here to here. Okay. So, epsilon will not change, C will change accordingly. So, your absorbance, so if this is when the pump pulse, the probe pulse comes, absorbance will decrease proportionate to the decrease in population, right. This way, as you change the pulse, as you change the delay of the delay between the pump and probe pulses, you generate essentially a map of the time evolution of the excited state population. That is how pump probe works. Of course, I hope we have discussed what happens when your probe is tuned to the absorption of the ground state and not the excited state, then you get something called ground state bleach. And if it is tuned to the absorption of an excited state that is formed as a result of excited state that is formed as a result of excited state process, then you are going to see a rise time. Okay. And let me also remind you, even though we have said it earlier, why is it that we are so obsessed with femtosecond? What is so great about femtosecond? And why not attosecond? Why not stop at nanosecond? We are obsessed with femtosecond because if you look at chemical kinetics once again, you are familiar with this Arrhenius equation, right. So, origin of that is Van 't Hoff equation in thermodynamics, and we are all very familiar with this kind of energy profile, right, where you have a reactant and you have a product and there is an activation barrier. Only when there is an activation barrier, you are going to have a temperature dependence of the rate constant, okay. And this is the activated complex. Study of activated complex opens up this field of molecular reaction dynamics. We are more familiar with the theory part of it perhaps from our MSc days, but what we are trying to do essentially is that we are trying to do experiments by which one can follow reaction dynamics, right. Now, if you have studied this activated complex theory and all, you would be familiar with this equation. Which equation is this? Eyring equation. So, Eyring equation expresses the rate constant in terms of the theoretical quantities, right. KT by H, K, where K is Boltzmann constant, What are the Q's? Partition function Q star divided by QA QB, where the reaction is A plus B two products kind of reaction, and e to the power minus E0 by RT, where your E0 is the activation energy. So, what can be the maximum value of K? Let us talk about the exponential part. What is the maximum value of the of e to the power minus EA by RT, and when do we get it? I want to know when K has a maximum value, largest rate constant. Largest rate constant would correspond to the smallest possible time associated with the reaction. Yeah. So, can you tell me what is the best possible value of e to the power minus E0 by RT? You are right, it is 1. And when does that happen? When E0 equal to 0. That means activation energy is 0. That is the best possible scenario, right. As activation energy goes higher and higher, reaction becomes slower and slower. Okay. Now, and so that would be 1 in the best possible case. What is the best possible case that I can get with the partition functions? Again 1. Okay. So, the largest value of the rate constant that one can get is kT by H, and at room temperature 300 Kelvin or something, this value turns out to be the value of fastest reaction. This turns out to be 6 into 10 to the power 12 per second. So, if this is rate constant, what would be the time associated with it, the reciprocal? Yeah, the time turns out to be 170 femtosecond. We have said it at the beginning of the course, just reminding you, 170 femtosecond. So, from theory, the expectation is that the fastest possible chemical process would require about 170 femtosecond. That is why femtosecond time scale is so important. That is why we want femtosecond pulses, because we expect that there is no chemistry faster than that. Nowadays, people study attosecond spectroscopy as well, but that is really state to state dynamics and all. It is very highly interesting, but chemistry sort of stops at femtosecond, and I will show you why we say that. Right. So, that is why this generated a lot of interest in 1970s and 80s and even 90s, and that gave rise to the field called femtochemistry. In fact, whenever you say femtochemistry, one name that would come to your mind, many names can come to your mind, but one name that definitely comes to your mind is Ahmed Zuhail. Ahmed Zuhail got his Nobel Prize in 99 for femtochemistry. In fact, he has some books named femtochemistry and femtobiology and so on and so forth. So, when you are talking about femtochemistry, it would only be proper to show you at least some of the huge amount of highly interesting and phenomenal results obtained in Zuhail group. So, I will show you just 2. This is not textbook material. You can find this in common physical chemistry textbooks like Macquarie and Simon or Atkins. Okay. So, the first piece of data, what is the question we are asking? We want to know, can we experimentally determine the rate constant of the fastest possible chemical process? What is the fastest possible chemical process? Breaking of a bond. How much time does it take? To study that, many experiments were done. The data we are going to show you is photo dissociation of ICN. So, sometimes when you show data like this, people ask, oh, what use is this? Why ICN? Why not benzene? But these are all invalid questions really. This is demonstration of a phenomenon. You have to work with something that you can get the interesting result from. There is no point asking why are you not taking a more complex molecule. For a more complex molecule, perhaps things would become more complicated and you would not understand. So, this, even though ICN is not a molecule that you encounter every day, the reason why ICN was used is this. The energy diagram of ICN is like this. So, you have this bonding anti-bonding kind of energy diagram, right. You have this first electronic excited state which has a minimum, and there is this excited state that is dissociative. I hope you are familiar with dissociative excited state, dissociative states, electronic states that do not have a minimum. So, you populate it, what will happen is that the molecule will break, and it is well known. By that time it was well known that if you excite by 306 nanometer or any wavelength that takes you here, then you can go from the bonding lowest energy state to a dissociative state, and the dissociation takes place like this, I plus Cn. Cn bond does not break, IC bond breaks. Okay. So, what are the photo dissociation products? I plus Cn. Let us not worry about the term symbol at the moment. And also this is a pump probe experiment without a probe. So, maybe you can call it only a pump experiment. It is a without a probe, because well, one can use a probe, but the good thing is it is also known that if you look at the Cn fragment, that can be excited, well, that can be excited by 388 nanometer. It is not a pump experiment, pump probe experiment, but you look at something different. So, here the probe is also acting as a sort of a pump. What happens is, first you have a 306 nanometer pump, you populate this state, and then the probe light is tuned to 388 nanometer. So, 388 nanometer is a wavelength that causes a transition of Cn to Cn star, and there is a corresponding emission. And as we know, it is easier to look at emission than at absorption. Will you agree with me? Because when you look at, when you do emission spectroscopy, even one photon is enough. When you do absorption, it is all about difference in absorbance. So, you have Avogadro number of molecules, even if 1000 molecules are excited, that may not be good enough change in absorbance. But if even one molecule emits, right, your comparison is darkness, which is 0. So, even 1 divided by 0 is infinite. So, what they did is that they looked at not at transient absorption as such, but they looked at the emission of cyanide star, excited state of Cn, which arose due to excitation of the Cn fragment by the probe light at 388 nanometer. So, same pump probe geometry, pump has 306 nanometer, probe has 388 nanometer, and you will observe that these are all ultraviolet colors, right. And the lasers they used at that time, I think they used Tisafy laser also, but mostly that time the lasers they used are the type that we have not even discussed in this course. They are called CPM lasers. It is colliding pulse mode laser. That was the technique by which ultra short pulses were produced before the advent of titanium sapphire lasers. Good thing about Tisafy laser is that it gets mode locked by itself. Just have to disturb it a little bit, and you have to give it the big enough cavity. But before that, in the era of dye lasers, you had to actually make these laser pulses collide with each other and form ultra fast pulses. It was a much more complicated technique. So, using this laser, what they observed was what is called laser induced fluorescence. And since pulse lasers were being used, they could follow the dynamics of laser induced fluorescence. Okay. What do you expect? What kind of time evolution do you expect for the laser induced fluorescence in this graph? See, the moment you excite it, should you get any laser induced fluorescence? No, because the ground state is what? ICN molecule. When you excite, at the moment of excitation, you still have ICN. Then it takes some time for the IC bond to break. And as the IC bond breaks, the emissive CN fragment is produced. So, what you expect to see here is a rise, okay? And that is what they observed. I have dramatized a little bit, but they did observe a rise in the laser induced fluorescence signal characteristic of this CN star fragment. Okay. So, what do you observe? You observe that the photodissociation is complete. Look at the times here. This is 0 time, this is 1200 femtosecond, 12 picosecond. In fact, if you go here, from here onwards it is flat, right. So, within 600 femtosecond, the fragmentation is actually done. Yeah. And when you fit it to a rise, the time constant that you get is 205 femtosecond plus minus 30 femtosecond, hence proved. Expected value is 170 femtosecond, experimentally observed value is 205 femtosecond plus minus 30 femtosecond. So, this is a very good match, as good as it gets between experiment and theory. Okay. So, this is a phenomenal result, because this vindicates the theory and tells you, gives you the evidence of how much time it actually takes for the bond to break. The fantastic result. In fact, this perhaps would have been good enough for his Nobel Prize. But then they actually studied many other things, and they tried to understand this process in very great detail, and they obtained what they called snapshots of bond breaking. Perhaps I should have dramatized this slide a little more, but since I did not, I will just explain from here. So, what they did is they studied many different molecules. One of the things they studied was NaI, sodium iodide. Okay. Now, let me ask you a question. Everybody has done flame test? Yes. What is the color of flame that you get for sodium? Yellow, right? What is the color of sodium vapor light? Sometimes there in street side, now it is being replaced widely by LEDs, yellow, right? So, that yellow, I think everybody knows about sodium D line, is not it? It is used in your polarimeter and all that. Now, see, this yellow light is actually characteristic of sodium Na, not Na plus. But then you take some sodium chloride and put it in flame, you get yellow color, which is characteristic of Na and not Na plus. Why is that so? That is so because you have this kind of an energy diagram here. You have NaI, which is called covalent, and then you have Na plus plus I minus, ionic one, and of course, the ionic one has a lower energy. This is Na plus I is actually dissociative, right. But then what you see is, if you can populate this somehow, then you will get this characteristic sodium light, sodium D line. So, that is what happens when you heat and all, when you put it in the flame, from Na plus I some amount of Na is formed, and that is what gives you the yellow color, again emission. So, what they did was, they took Na plus plus I minus and then they excited using a laser pulse, and they used a laser pulse that would take the system from Na plus plus I minus surface to Na plus I surface, okay. That is dissociative. So, you can think that the moment it is taken to Na plus I surface, dissociation would have taken place, okay. So, if you follow the same transient absorption, what should you see? You should see a rise for free Na absorption, and you should see a decay for NaI absorption, right. What they see is this, and it is extremely, it is not, it is extremely, let us not say difficult, but it is extremely non-trivial to get data that looks like this. This thing that you see is not noise, this is real data. What you see is, for NaI absorption, yes, there is a decay, but the decay is associated with oscillations. For the free Na absorption, there is a rise, but the rise is associated with oscillations, periodic increase and decrease. Why is that so? That is so because, once again, we will not go into the intricate details of this, but this is something that anybody working in the field of ultrafast dynamics should know. So, I encourage everybody to read papers on this, papers and books. So, what happens is, remember the property that we studied of ultrafast pulses? How do you produce ultrafast pulses? What is the technique? Mode locking, is not it? So, when you mode lock, what happens to the spectrum? The ultrafast pulses, are they monochromatic, or do they have a broad spectrum? They have a broad spectrum, right, because as many modes you lock, shorter pulse you produce, more modes you lock, shorter pulse you produce, okay. So, what happens is, when you excite using an ultrafast pulse, then let us say this is your ground state. Of course, here it is a dissociative state, but it is easier to understand if it is, if the excited state is also something that goes to a minimum. So, the states are associated with these vibrational levels, and you know the V equal to 0 state is the only one that is populated at room temperature. So, if you excite using a highly monochromatic light, then you can go from V equal to 0 or V equal to 1 or V equal to 2, whatever the energy is. But then if you excite using a broadband light, light that is the light your ultrafast pulses, then you cannot selectively excite to 0 dash, isn't it? You cannot selectively excite 1 dash or 2 dash. You end up populating many of these levels to different extents, right. So, what is the wave function of the lowest one like? Something like this. The one above that is something like this. One above that you have one more, so on and so forth. Okay. So, what you do is, and all these states get populated at the same instant, right. So, what you form then is not a particular wave, but a wave packet, a coherent wave packet. A wave packet means a packet of waves, you can think like that. When the wave function is not a single wave function, but really a superposition of many wave functions, then it is called a wave packet. And you know what happens when you superimpose many waves? What will happen? Localization will take place, isn't it? That we have, I think, discussed earlier. At time t equal to 0, if they are in step, then as time passes, then they will get out of phase. So, you will end up getting something like this, all right. And more the number of waves you mix, narrower will this distribution of the wave packet be. So, once again, for a fundamental idea of wave packet, you can read something like Atkins. In fact, they have used the idea of wave packets to discuss uncertainty principle, where they talk about momentum waves. It is an interesting read. I encourage you to do that. So, when you excite using an ultrafast pulse, you end up creating wave packets, and wave packets are not stationary, they oscillate. Okay. So, that gives rise to this interesting phenomenon called coherent wave packet dynamics. Okay. I will not go further into that, but just be aware that here we have an example of coherent wave packet dynamics, which is a very important field of study in ultrafast dynamics. I encourage you to read up on that. And essentially what it means is that the oscillations mean that you have produced this. So, you see this is a wave packet. Okay. Now, this wave packet oscillates between Na plus plus I and Na plus I. That is why there is a rise, but then there is a fall as well. Why? Because it had dissociated, now it is coming back. Then it dissociates again and it comes back. So, the system oscillates post excitation between a dissociated and undissociated state, and that is what gives rise to oscillation in this signal as well. And this oscillation has a period of 1 picosecond or so. So, it is not as if you break the bond and that is the end of the story. Breaks, gets made, breaks again, gets made again, and finally, it does not come back after a point of time. It is like a damped oscillation. Okay. So, this is the extent to which you can follow molecular processes using ultrafast techniques. Okay. You can get snapshots of bond breaking, and that is what got Zuel his Nobel Prize. So, we stop here now, and we will come back and we will talk about another phenomenon.